let's take a look at electrical cells and batteries. An electrical cell is a device which creates an EMF that we use in a circuit to cause a current to flow. The most common version of an electrical cell uses chemical reactions to create the EMF. And if you want to know more about those chemical reactions, feel free to take chemistry. We're not going to address that right now, even though there is a lot of interesting stuff going on inside. If you take a bunch of electrical cells and combine them to create a greater EMF, that's what a battery is. A battery is a combination of electrical cells, and that is reflected in the diagram of both of them. The electrical cell is drawn like this, and a battery is supposed to represent multiple cells together, so it's kind of like two little electrical cell symbols next to each other. Cells are categorized as either primary or secondary. A primary cell is one where it cannot be recharged. You use it once and then you're done. So this is like a AA battery that you buy and you put it in your calculator and you use it, and once all of the chemical reactions inside there are complete, it no longer provides an EMF and it's no longer useful. A secondary cell is one where the chemical reactions can be reversed and the battery can be recharged. So in a secondary cell, you use it to provide an EMF. All the chemical reactions happen. Once all the chemicals have been used up, you can undo those chemical reactions. And if you undo the chemical reactions, then the chemical reactions can happen again and the cell can provide an EMF. The way that you recharge a secondary cell is by sending a current through the cell backwards. So normally, the current would go from the positive terminal around the circuit into the negative terminal, like that. In order to recharge the battery, you just got to send it the other way. This reverses the chemical processes in the battery. We're not going to worry exactly how that happens, but it does it. And that adds energy back into the battery. So this costs some energy to do. It's storing energy back into the battery by putting it into chemical potential energy. And the battery will store the energy that way until it's placed back in a circuit, and then the chemical reactions start to happen. It creates an EMF, and that drives a current going around in the circuit again. There is a common quantity used to describe cells and batteries called the cell capacity, and it's a measure of the cell's ability to release charge. Its unit is in amp hours, and it's the current output times the time it can maintain that current output. That's the definition of the capacity. So if a cell has a capacity of 10 amp hours, what that means is that it can supply 10 amps for 1 hour. Or it could supply 5 amps for 2 hours. Or it could supply 2 amps for 5 hours. Or it could supply 1 amp for 10 hours. In reality, it is more complicated than this, but this is a good first step in understanding cell capacity. Now, after the cell has been used, its ability to output an EMF and create a current will go down. And this is true for both primary and secondary cells. I'll draw a little graph to describe what I mean. It'll be cell EMF versus time. So you can see that the cell starts out with a high EMF. It's able to provide a large amount of EMF. It's kind of the maximum EMF that you would expect from the cell. As time goes by, its ability to provide that EMF will slowly decrease over its lifetime. And towards the end of its lifetime, there's a quick drop-off in the EMF that it's able to provide. And at some point, the EMF that it's going to be able to provide is not going to be enough for its function. So this is kind of like if you have a TV remote. At the beginning, works great. It provides plenty of EMF, but at a certain point, the battery is going to get old, and it's not going to be able to provide the EMF that's necessary to work the remote. Now with secondary cells, there's an additional complication. Turns out that the more times you recharge a secondary cell, the lower its capacity becomes. And you often hear this, especially with cell phone batteries, where we hear that the rechargeable battery can't keep its charge anymore. And that's what's happening. The more times you recharge a secondary cell, the less effective it will be at providing the EMF that it did when it was new. Now, batteries and cells are real physical objects. They're not perfect, ideal things. And in reality, batteries and cells are imperfect things. They do not provide the EMF that we would always expect. And a good way to model this imperfection of cells and batteries is with something called internal resistance. And with this model of an internal resistance, we think of a cell or a battery as an ideal cell or battery in combination with an internal resistor. So I'll draw a diagram of this. Everything inside of the dotted line is representing the cell or battery. And this little resistor here, that's the internal resistance. And don't think that an internal resistance is a real thing in the sense that if you open up a battery, you'll find that someone has carelessly put a tiny little resistor inside of your battery. No, this is a model of what's happening. This is a way to represent the imperfections in batteries and cells in a relatively simple way. But if we use this model, which works pretty well, when current flows through a cell, then there will be a potential difference across this little internal resistance. And that is going to decrease the potential difference across the terminals of the battery. So I'll show you what I mean. The potential difference provided by the battery equals the EMF from the ideal battery minus the potential difference that's lost to the internal resistance. And the potential difference that's lost to the internal resistance is equal to the current times the resistance of the internal resistance. So the potential difference that you actually get from a cell or battery is equal to the ideal EMF that you would expect minus I times R, where R is the internal resistance of the battery. And if you look at that expression, if there is no current coming out of the battery, then the potential difference provided by the battery is equal to the ideal EMF. So if you used a voltmeter to measure the potential difference across a battery, which is not in a circuit and not providing any current, the potential difference that you would measure would be the ideal EMF. Once you put that battery into a circuit and it starts providing a current, what you will find is that if you measure the potential difference across the battery, it will be smaller than the ideal size. It will be smaller by an amount IR, where I is the current coming out and R is the internal resistance of the battery. And you can see if the internal resistance of the battery is greater, then you will get a smaller potential difference from your battery. So a terrible battery would have a large internal resistance, and as soon as any current came out of it, you would get a significantly reduced potential difference from the battery. A good battery would have a small internal resistance, so that even if it provides a large current, the potential difference from the battery is going to be very close to the ideal EMF. But either way, if you have an internal resistance, you would expect that as you provide more and more current from the battery, you expect the potential difference across the battery to get smaller and smaller.